before wiping the board, I need to go through this. So we're given this relation. We don't yet know whether it's an equivalence relation, so that's what this is about. Well, here, we're to prove that. So, so the relation is this. So A inverse B belongs to H. If that's the case, then these two elements A and B are, that's the relation they have. Now, is it an equivalence relation? So if it is, then this relation will be reflexive, symmetric, and transitive. Okay? The definition of an equivalence relation, special kind of relation. All right. So let's try to prove: is it reflective? So does A tilde A, is that true? Does that work? Well, for any element belonging to your subgroup H, you'll have this will be true. That A inverse A is just E. Now E belongs to your subgroup H. Any subgroup has to have a unit. Okay. So therefore A inverse A belongs to H, and that's of this form. So instead of having B here, you have A. So A inverse A belongs to H, and therefore A tilde A. So you have this, right? Therefore, this relation here is reflexive, so that's okay. Tick. All right. Now, for symmetric, so if you have A tilde B, can you derive from that B tilde A? So let's try to do that. So if we have this, if A is if there's a relation A and B, if that's true, then A inverse B, by definition, right here, belongs to H. Now, if that belongs to H, it's just an element, right? H is a subgroup, so it's still a group. So each element here, this product, will have an inverse. So therefore, the inverse of this belongs to H. But what is the inverse of this? Well, it's B inverse times A inversed inversed. So just A. So B inverse A. So that belongs to H, and that means so B inverse A. B inverse A. So that means that B tilde A. So, okay. So if A tilde B, therefore B tilde A. So therefore this relation is symmetric. So tick. So that's the second one. All right. Now, if A tilde B and B tilde C, can we prove that A tilde C? In other words, is this relation transitive? Okay. Well, if A tilde B, if there's a relation between A and B, then we have this. Right? So A inverse B belongs to the subgroup, and if that's true, then B inverse C belongs to the subgroup. That's the definition of that. Okay. Now, this is just an element of H. This is also just an element of H. So we can multiply the two, and since H is subgroup, hence a group, therefore it's closed. Right. So therefore the result of this element times this element, which is this, that also belongs to H. Okay. Because H is a subgroup, it's closed. Now, what is this? Well, the B's and B inverses cancel, and you're left with A inverse C. Right? Therefore, A inverse C belongs to H. And, well, that is of this form, except you have a C here. Right? So A tilde C. And there you've got it. So A tilde B and B tilde C, therefore A tilde C. So that this relation is then transitive. Okay? So that's the third one, third condition. So you've got all three reflexive. This relation here is reflexive, symmetric, and transitive, and therefore it's an equivalence relation, right? Because it satisfies those three conditions. All right. So now we know that this is an equivalence relation, and that's a prerequisite for proving these two properties. So now I can clean the board.